latent heat of vaporization, specific latent heat of vaporization. We're going to be putting water in a kettle and boiling it, getting boiling point, so it starts to vaporize at constant temperature, and we can monitor how much vaporizes on the mass balance, and we can measure the energy input on here. That's going to be in kilowatt hours, but we have to convert kilowatt hours energy into joules, and multiplying by 3.6 million. And then we can time on here as well. So the specific latent heat of vaporization, LV, here, and this is the heat energy we're putting into the water, Q. M is the mass of the water that we're going to vaporize, and LV, latent heat of vaporization. Makes more sense like this. LV is the heat energy input per unit mass. So in other words, it's the energy required to vaporize 1 kilogram of liquid at constant temperature is the latent heat of vaporization, specific. Now, in terms of change of state, we're putting in energy Q and to a liquid. Now, liquid, I've done little bonds between there, they're moving around, but there's a traction between the molecules, but they're quite close to each other. Now, what happens at the boiling point, the bonds start to break, and the energy that we're putting in is breaking the bonds, not raising the temperature. So the kinetic energy doesn't increase. We just end up separating the particles like this. So they're now moving around, and they have the same temperature. So breaking the bonds at constant temperature, the energy we're putting in is breaking the bonds, not raising the temperature. So what we're going to do is put 100 ml of water into the kettle. And make sure we can see everything. Okay, need to reset our stopwatch. And we also need to reset the energy meter here. So that's on power. We want it to be on kilowatt hours, and it's on 0. Now, we also need that to be on 0, so it will tell us how much we've lost. There we go, it doesn't have to be that precise. Let's do it. There we are. It's on 0 now, and hopefully we can see that temperature goes up. I'm going to heat the water now, and you'll see the temperature. It was already quite warm. You'll see the temperature go up to, it should be just over 100 because it's not pure water. It's 101, 102 perhaps. There it goes. And you can also see the energy going in, kilowatt hours. Now, it's boiling at the bottom anyway. So I'm going to switch that off now. I've stuck some blue tack over that, which has stopped the steam from switching the kettle off, hopefully. And now it's got quite warm. Why is that gone up? Probably because of the cable. So I need to turn that back to 0. So we're starting it at 0. And this also now needs to be reset back to 0 kilowatt hours. And make sure we can see everything. I'm going to reset that again. It's changing. Now, what's going to happen now is I'm going to video this about here, and then you can take down readings on a table like this. Just so you can see the table, we've got time, energy in kilowatt hours, energy in joules or kilojoules, whatever it comes out as, multiplied by 3.6 million, and then mass vaporized in grams, and then we monitor the temperature at the end there as well, which of course should stay the same. And we're going to go for, let's go for 200 seconds and see what happens. So now, without further ado, let's see if we can get this working. So all I need to do now, I'm going to switch it on, hopefully without moving anything. Then as it starts to boil, I'm going to start stopwatch now, and there we go. Take the first reading after 20 seconds. So 20 seconds, that's 0.08, I think, on the hour meter. We're going to go for 40 seconds and take down the grams loss. It's losing quite a lot of mass quite quickly, isn't it? 40 seconds. Let's see what's happening to temperature. We probably can't note down the temperature, but yes, it's over 100. And we're going to be going for 60 seconds next. There it goes. Okay. And again, temperature's the same, about 105. And what are we going for now? Ooh, next one is now. And temperature. Okay, 105, 106. I'm doing 140 seconds next. Okay. We can move from there a bit better, can't we? Perhaps. And what's on now? We're going at 160. And now, that's fine, like 54 grams. Half of it. It's boiling furiously. And there's the temperature. And then 220. I think we've got over. Well, it did switch itself off, but it's pretty good because that's where we wanted it. So hopefully you got some data there. We got a total of 46. I mean, you could take 0.002 or 3 off each measurement, because I think by the time we started the stopwatch and switched on, you probably had about 0.003 on there before it was at boiling point. So you might want to do a correction there. And we've got still creeping up as a bit more vapor comes off, but we vaporized about 66 grams. And you can see the temperature's dropping again now, but it did stay about 105. Although we didn't quite manage to monitor that effectively. So that's the specific latent heat of vaporization. What you need to do now with this data is you've got to basically, you can draw a graph, because if you've got our equation Q equals ml, got our equation Q equals ml, then if we were to draw a graph of the energy input, the total energy input there, against the total mass that's been vaporized, then of course Q and the mass vaporized should be proportional. We should be plotting hopefully data like that in a straight line. And of course the gradient, the rise over the run, the gradient should be L. Okay, so change in Q over the change in mass should be equal to the latent heat of vaporization. And that's quite an accurate way of calculating that. Okay, so we'll bash at that on graph paper.